CFD Research, in collaboration with the U.S. Army Research Institute of Environmental Medicine, presents a comparison of Vertex-influenced weight algorithms for the repositioning of 3D medical models. The tetrahedral meshes used in this work were created by Usarium from the Virtual Population Dataset from the ITIS Foundation in Zurich. The imaging data were segmented to identify tissue types, and the images were tetrahedralized to produce a volumetric mesh with fully labeled tissues and organs. The mesh consists of 160,038 vertices and 869,993 tetrahedra, or cells. For each cell, one of the 76 different material types are assigned. This mesh is a low-resolution version with a resolution of 5 mm. Rigging and skinning are commonly used techniques in animation to reposition surface meshes. The basic idea is to define an underlying skeleton by specifying joint centers and segments which connect them. For our 3D volumetric meshes, we calculate cell intersections with the segments and assign influence weights to each vertex for each segment. We compare two different methods of bone influence weight calculations: a material-naive method, in which all materials are treated equally, and a material-informed method, in which all selected rigid material weights are selected to be non-deformable, and a Laplacian diffusion is applied to ensure a continuous displacement field. The mesh can then be repositioned by specifying joint angles manually or through motion capture data. Both of the methods require a one-time weight calculation. The calculation time for the material-informed method is longer than the material-naive method due to the Laplacian smoothing. The computation time varies based on the error tolerance set for Laplacian smoothing. A lower tolerance will produce better results at the cost of increased computation time. Here the error was set to 0.01 and the computation took around 70 seconds. Once this is complete, the influence weights for the skeleton and mesh can be saved and loaded to avoid running this calculation again. The mesh repositioning itself happens in real time. We tested the algorithms in several major joints: the knee, hip, and shoulder. In this poster, we present results from a 90-degree shoulder abduction, which are representative of the results at the other joints. In the images in the middle of the poster, individual tetrahedra are visualized and shaded to show the change in volume for each. Cool colors represent little change in volume, warm colors represent a large change in volume, and purple represents the most extreme changes in volume above 100 cubic millimeters. For the material-naive method, note the large deformations far from the joint center. These are likely cells on the edge of influence of the upper arm segment. One may also observe many cells in bone-labeled tissue which are greatly deformed. In the material-informed method, notice the bone-labeled deformation is largely around the joint center. Future work hopes to remove this deformation completely. Visually, the material-informed method produces more desirable results in both bone and muscle-labeled tissue. The table shows the mean tetrahedra material volume change for all the tetrahedra in the mesh. Notice the reduction in bone-labeled material deformation in the material-informed method when compared to the material-naive method. The mean muscle-labeled change in volume is almost the same in both methods. However, we can visually see the distribution of deformed cells in the informed method is more desirable than in the naive method. These results indicate that the material-informed method reduced the unwanted deformation in rigid structures such as bone. The remaining stretching only occurred around the joints. In the future, we will investigate methods such as mesh segmentation to eliminate this stretching. Although this method lacks the fidelity of physics-based finite element methods, it is a computationally efficient method for quickly repositioning medical models for further post-processing and analysis or application in medical visualizations. Furthermore, the method can be applied to any tetrahedral mesh composed of labeled materials. In summary, animation-inspired mesh deformation techniques can be applied to 3D medical models for finite element applications such as thermal analysis and projectile penetration. If you have any questions or would like to speak further with the authors of this work, please reach out to us at timothy.zehnbauer@cfdrc.com.